Hey everybody, it's Professor McDonald. I'm recording answers to your questions because I won't be able to hold class tonight. So I hope this helps, and please follow up with me if you still have questions, or get with a tutor and earn some extra credit while you're at it. This first question is from lesson 8. It's number 3. I'm going to go ahead and label my sheet here. L3 number, oops, I had that backwards. Number 8, lesson 8, number 3. And there's a couple of parts to this question, and the first part of it's easier than the second part, but we'll go ahead and talk about both. I'd also like to point out that we have in our reference packet for test 3 some instructions about how to use Excel to answer questions involving normal probability. Okay, and we do have also a Z table in here, so that if you don't feel comfortable using Excel, this is another way that you can get your answers. Or you can even just do this because you want to check your answers. So maybe you could learn to do both. All right, so the question here says, sketch the region corresponding to this statement. The statement is that we want the probability that a z-score, a standardized z-score, so standardized scores or z-scores, and they have a mean of 0 and a standard deviation of 1. And we want to know that this z-score might fall between 0.3 and 0.6 with what probability? If we randomly chose a z-score from this population, what is the probability that it would be between 0.3 and 0.6? So when it's a between area like that, we'll choose between two values, and we'll simply line it up with the values. So on the left, we'll put it at 0.3, and on the right, we'll put the right boundary at 0.6, and that shows us what we're looking for, this little sliver here. And then we're going to actually find the probability and enter it. So we have our lower boundary and our upper boundary, and then we'll put those numbers here. Okay. Now, what we can also do is just move this over, and those are our z-scores, but what are the probabilities that go with those? So what's the probability of getting something that's less than 0.3, for instance? And then what's the probability of getting something that's less than 0.6? Getting the probability of something that's less than 0.3, we use norm CDF, norm.dist, the cumulative distribution function, with the boundary of 0.3 first, then the mean of 0 because it's a z-score, and the standard deviation of 1 also because it's a z-score. And always true for cumulative. Remember when we did binomial distribution, sometimes we chose false and sometimes we choose true for cumulative with the binomial distribution. For normal distributions, we will always choose cumulative, true. Okay, and we're going to do the same thing for this one. Whoops. We can actually copy that over here. All right, so notice that the area from the left from the larger, here's my larger boundary, 0.6, it has a larger area from 0.6 all the way to the left. That's the way norm.dist works. It always gives you the area to the left. And if we look in our table in the packet, in the positive z-score table, which is set up to give you areas to the left of any positive z-score, we line up 0.6, 0.60 in the table, we see we get 0.7257, which is the same answer that we get here when rounded to 4 decimal places. Okay, so I'm just going to put that here for the table so that we have a reference to both. And then from 0.3 as a z-score, we get 0.6179. Same thing when you round it to 1 decimal place. All right, so now what I wanted you to notice is that area to the left from 0.6, from this boundary all the way to the left, is of course larger than the area from this boundary all the way to the left. Now, all we want is the little sliver where they overlap. So by subtracting these two, we get the little area right here in between them. So we're going to go ahead and do our between area by taking the larger left area minus the smaller left area, right? And then we'll just enter it. If we were asked to give it, we would, but we don't actually have to give it here. We were just supposed to show where the boundaries are to make that shaded region. But in some problems, you'll have to actually find that area. All right, now the second part of this is to shade or sketch the region corresponding to this statement. We want the probability that z is greater than some constant, and we want the area, which is the probability, to equal 0.15. So in order to know how to get this boundary in the right place, we are going to have to find the actual z-score that should be going here. And we can do that with norm.inverse. So here in our reference packet, we have objective 2, finding a boundary, or either an x or a z. Looking for a z-score or an x value, we can use norm.inverse, put in the left area, the mean, and the standard deviation. Okay, so for this problem, we know the mean is 0 and the standard deviation is 1 because it's a z-score. The left area depends on the situation here. Well, this greater than symbol means we're shading to the right, and that the area to the right is 0.15, which is less than half, so we know it's over here somewhere. Okay, but we want to know exactly where to leave this slider. Now, if the area on the right is 0.15, then the area on the left must be 0.85. So I'm going to come in and let's just take a little snip here so we can draw on it a bit. Okay, if this area over here, well, if this area on the right is 0.15, then this left area, which is the complement, and the whole area has to add up to 1, so this would be 0.85. So to find what this z-score is right here, I'm going to use norm dot inverse the left area of 0.85, a mean of 0, and a standard deviation of 1. And that's how I'm going to know where to put the slider, so that I'll get an area on the right of 0.15. Okay, so norm dot inverse probability 0.85. Remember, that's always a left probability. The mean is 0 and the standard deviation is 1. So I need to line up to 1 decimal place. I need to slide up, line up my slider at 1.0. And this one, I guess I moved my slider by mistake. It was supposed to be at 0.3 and 0.6. Okay, so that's how you answer that. And you can get different versions of it. The top one is usually pretty easy. Just notice this symbol. If it's to the right, then you just line your slider up to 0.2, and you're done with that part. Just pay attention to the symbol so you know if you should choose right, left, or between. Down here, we have now a between area, and we want the area in between the two values to be 0.2. Now, since it's negative c and positive c, that means they're the same distance from 0. So let's just assume for now that it's -1 and +1, which that probably isn't a good guess. Remember the empirical rule? The empirical rule said that we expect 68% to be within 1 standard deviation of the mean. Z-scores are standard deviation, so there should be about 0.68 area in between -1 and +1. So think about that, 0.68. So 0.2 is less than a third of that. So probably these are going to be in pretty close to 0, like maybe -0.2 and +0.2. But we don't need to guess, we're just getting a rough image so that we can have something to visualize while we figure out the real answer. Okay, so I used a little knowledge I had to help me kind of think about what the answer could be. But all we're going to do now is we're going to assume that if the total area in between them is 0.2, okay, this area is 0.2, then on each half of it is 0.1, right? So that would mean that if we cut things right down the middle at the mean of 0, and then I went to my left negative boundary, -c, then this little area right here would be 0.1, half of 0.2. And since from the mean all the way to the left is 0.5, then I would know the rest of this area would be 0.4. So to figure out what -c is, I can do norm dot inverse on 0.4 with a mean of 0 and a standard deviation of 1. And that'll tell me where to put my negative value and my positive value. So norm dot inverse on 0.4, mean of 0, standard deviation of 1. And so I'm getting negative, to 1 decimal place, that would be -0.3. So I was kind of close. Just stretch this out to -0.3 and +0.3. And there you have it. Another way you could have figured out that this area was 0.4 here. So remember, you always got to feed a left area to the norm.inverse command. Another way you could have figured it out is if the whole area under the curve has to be 0.1 and you subtract this small in between area, you would get 0.8. And then half of 0.8 is going to be on each side. So half of 0.8 is 0.4. That's another way you can figure it out. Whichever way is more intuitive. Should we try one more of these? There's another between. I think that's the same one. Let's see. Yeah, another between area here. So again, take this area. This is the harder part, so I'm just focusing on this. Now we have a bigger area, 0.7. So it is going to be somewhere like right around -1 and +1. Because we already know 68% lies within 1 standard deviation of the mean. So I'm guessing it's going to look like this. Now, if this blue region in between is 0.7, then the total of the two white tails is 0.3, and half of 0.3 is 0.15. So to find the answer for this part, all I have to do is norm.inverse for 0.15, mean of 0, standard deviation of 1. So as you can see, it's -0.04, or if you're rounding to 1 decimal place, that would be -1. So because we're rounding to 1 decimal place, we actually end up right there. And then this one was between area, -1.4 and +1.4. So we're done with that one. Okay, and it can get pretty quick the more times you do it. Here we have a right area. The area is 0.3, which is less than half. So I know I have a positive z-score somewhere over here. So if this side is 0.3, this side is 0.7. And I don't have to split it in half because there's only one side I'm looking for here. So norm dot inverse on 0.7 with a mean of 0 and a standard deviation of 1. So that's about where it should be, 0.5. You round this to 1 decimal place. And on the top part, which I kind of skipped over again because it's easier. I don't know why, I just always go to the harder part. Left of the value, yes, because it's a less than symbol. So we do want a left area. This left area of 0.6 is greater than half, so I do think my slider is going to be... Oh wait, I'm thinking about the second part of the problem. For this one, this was the different kind, where we're shading, we're given the boundary, and we're just shading the area by placing the boundary in the right spot. So 0.6, right about here. There it is. Okay. Okay, the next question on here. Assume that the readings at freezing on a bundle of thermometers are normally distributed with a mean of 0 and a standard deviation of 1. A single thermometer is randomly selected and tested. Find the probability of obtaining a reading between these two temperatures. Right, so you're finding a probability, a between area. Okay, so since we have these thermometers, which normally read at a mean of 0, standard deviation of 1, what we have are z-scores. Okay, so we're using the z-score table or Excel to answer these questions. And just like before, in the previous question, it can help to see a sketch. I always recommend sketching these things out, even roughly. And this actually goes farther than -3, so I'm going to bring in my boundaries a little bit. All right, so now I'm going to mark the values given in the problem. We have -3.237, -3.32237. Okay. And then we also have one at 1.66. And then we're going to shade in between. Now to find a between area, you want to find the left larger area than the left smaller area. And then you want to find the between area by subtracting the larger left area minus the smaller. So I'm first looking for the larger left area, which is going to come all the way from over here, all the way back towards infinity. And to find that, I'll do norm dot dist, and then I'm going to put in my boundary of 1.666, then the mean of 0 and the standard deviation of 1, and true for cumulative. And I'm going to do that for the smaller area, but I guess we'll do one at a time here. Okay. Okay, so that larger area is 0.95213. Now I'm going to do the other area. Let me go back this way. And this one I'm going to do in a different color right after I put this back. All right, now I'm doing just this area from here. Oh, not that area. From this little boundary, this little tail over here. So that little tail, which is the tail we don't want. 0.95 is this red region all the way back towards infinity. But remember, we only wanted to go as far as this little boundary here. So we're getting rid of this orange tail. So the orange tail, we're going to get that doing norm.dist, norm.dist on -3.237, the mean of 0, standard deviation of 1, and of course true for cumulative again. And you can also put a 1 in to say true for cumulative. You don't have to always type the word true. 1 means true, 0 means false. So I have -3.237, mean of 0, standard deviation of 1, and we'll use 1 to choose true. All right, now we find the between area, where we just subtract the larger region minus the smaller tail, and this should be our answer here. Okay, and we could have also found each of these two pieces using the table by using the positive z-score table on 1.66. That would be, here's 1.6, and then up at the top where it lines up with, I guess I would round that to 7, 1.67. So I would have found the answer here, 95.25. As you can see, that's pretty close to this. Or if you rounded it down to 1.66 and you went to 1.66, that would be 95.15 or 0.9515, excuse me, 0.9515. Or since it is somewhat in between, you could have averaged those two numbers to get closer to this number here. But as you can see, norm.dist is much more accurate than the table because the table only goes up to 2 decimal places. So there's going to be some round off error. But my guess is that if we had tried using the one that when you round it to 1.67, you get 9.9525. 0.9525. And then for this other one, negative 3.24. Let's look up negative 3.24. Negative 3.24 would be in this column here, 0.0006. So when I subtract those, the larger minus the smaller, the answer is very close here, especially when you round it. And usually the homework will accept either answer. So if I were to put in 0.95, I don't know if it'll let me even try it like this once I've already got it right. Well, it didn't like that table way, this particular question. I wanted a more accurate answer. Yeah, so for some of these, it really is safer to use norm.dist in Excel. But on a lot of these, it'll accept either one. So that was number 12 from lesson 8. We also had that question from Nemi. So I'm going to go ahead and mark that one already. Then we have another one, number 16. Assume that z-scores are normally distributed with a mean of 0 and a standard deviation of 1. And find B. Okay, this is like that first question we did tonight, where you know what the area is, but you need to find the boundaries. And it's a between area with the boundaries being negative b and positive b, which means they're the same distance from 0. So again, all we have to do is take 1 minus this, and then half of that, and then use norm.inverse. So 1 / 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 × 2 We're given some information. Mean of 0, standard deviation of 1. Between here and here, we have 0.9196. So since the whole area under the curve is 1, if you subtract 0.9196 from 1, you get 0.0804. So the two little white tails have to have half each of that. So let's divide that in half. And that's this side over here will have an area of 0.0402. And also this side over here will be 0.0402. And if this is negative b and this is positive b, we can use this left area with norm dot inverse to find b, negative b. Okay, norm dot inverse with 0.0402, mean of 0, standard deviation of 1. So b, negative b, is negative 1.74837. And that makes positive b the same number, but just not negative. Okay? So then following the round off directions, none are really given. So I'll just copy this in. Usually we give 2 decimal places for z-scores. But sometimes if you give more places, it'll still accept it. That was number 16. Number 15. About what percent of the area under the curve of the standard normal distribution is outside the interval from negative 3.03 to positive 3.03? Or in other words, beyond 3.03 standard deviations of the mean. Again, remember z-scores represent standard deviations. Okay, so this is kind of a similar example, except for they've given us the boundaries. We got to find the area. So our sketch has z-scores. I know I don't make pretty sketches by hand, but hopefully you can just pretend that they're beautiful, symmetric. That one's a little better. It's just not that easy to draw on my slippery screen, which is upright. All right, so from negative 3.03 to positive 3.03, what is the area? And then we're going to turn the area into a percentage for our final answer. Okay, now the area, when you're finding between area, it's the same drill every time. Find the large left, then find the smaller left tail, and then find the between area by subtracting them. So the larger left area would be from the rightmost boundary, 3.03. So I'm going to do norm.dist. Remember, when you're looking for an area, it's norm.dist. If you're looking for a z-score or an x boundary on the horizontal axis, use norm.inverse. Norm.dist when you're looking for an area, a probability, or a percentage. They're all interchangeable. All right, so norm.dist, the boundary is 3.03. And the mean is 0 and the standard deviation is 1 because we're talking about z-scores. And we always say true for cumulative. Okay, now, Remember, the answer that you are given using this command is always the left area. Okay, now we're going to do it for the smaller side, this little tiny white tail over here on the left, because we need to cut this off of the larger region. So we're putting in negative, we're still doing norm.dist, but we're just putting negative 3.03, the mean of 0, standard deviation of 1. And again, true for cumulative. And subtract them. Larger minus the small tail. And there's your answer. Except it wants it as a percentage. So we can multiply this answer by 100, or simply move the decimal place 2 moves to the right. So this is going to give you the same result as multiplying by 100. Now, I didn't pay attention. Let's see. 99.7554. Well, maybe it wants it rounded. I don't see any round off instructions, though. Let's just try it to the nearest I'll go to here. Well, what's the answer supposed to be then? The area under the curve. Oh, I read it incorrectly. Notice that it says about what percentage of the area under the curve is outside the interval. Well, I found the part that's inside the interval. So what's the part that's outside it? That would be 1 minus. And then multiply that times 100 to make it into a percentage. Or you can also right-click and format it as a percentage. Or you can move the decimal place over 2 places. So all right, so I'm getting something closer to this. Let's see, 0.244554, and that worked just fine. That was number 15. We also had that question from a couple more students, and that was probably the reason it was popular is you have to read carefully. I meant to say the other way. Okay, the next one to look at, let's look at number, that's from lesson 9. Let me go back. I'm not ready for lesson 9 yet. All right, also from lesson 8, we have number 22. For standard normal distribution, find the z value that goes with the left tail area of 0.3052. Okay, so here's my sketch. We're looking for a z-score. There's a mean of 0, standard deviation of 1. We were given a left tail area of 0.3052. And since it's less than 0.5, you know this is going to be a negative z-score. This area 0.0, or 0.3052. There we go. So using norm.dist, remember norm.dist always gives you a left area, and that's what we're looking for. So all we have to do is put in, oh, wait a minute, it's asking for x, right? X could also be z. It just means a boundary. So if the information doesn't fit, you're probably using the wrong function. Norm.dist is what we're looking for when we're, or what we use when we are looking for a area, an area, a probability, or a percentage. Here we are given the area, so we're not looking for the area. So what's the other normal function? Oh yeah, norm inverse, which is what you do when you are looking for a boundary, and that is what we are looking for. We're looking for, it says find the z value that goes with the left tail area. So that z-score, that's your boundary. Put in the left area. Remember, it has to be a left area, and this one is, so that's good. That's a mean of 0 and a standard deviation of 1. So our z-score and we're done. That was number 22 from lesson 8. Number 23 from lesson 8. A manufacturer knows that their items have a normally distributed lifespan with a mean of 4.6 years, okay, and a standard deviation of 1 year. If you randomly purchase one item, what is the probability that it will last longer than 5 years? All right, so what this means now is we've been given the mean of 4.6 years, standard deviation of 1 year, and we want to find a probability. Which means find an area, which means use norm.dist. Okay. Now it helps to draw a picture. They said they wanted the probability that x, notice I'm not saying z this time because it's not a mean of 0 and a standard deviation of 1. Both of these have to be, the mean has to be 0 and the standard deviation has to be 1, otherwise it's not a z-score. It's what we call an x. It's a non-standardized value. And we want it to last longer, so that's a greater than, longer than 5 years. Okay, that's the notation, the proper denotation for the probability we're looking for. Okay, now we're using the normal curve with our x values across the bottom. The mean is not 0, that's force of habit. The mean is 4.6. And the standard deviation is 1. Okay, so if I go 3 standard deviations, 1, 2, -1, -2, -3. Now I'm only going 3 standard deviations in each direction because remember the empirical rule tells us that 99.7% of all the values will be within 3 standard deviations of the mean. Doesn't mean you can't have anything go beyond that. It's just most values will fall in that range. Okay, so all I did was take my mean of 4.6 and add the standard deviation 3 times and subtract the standard deviation 3 times. Just gives me a scale. to visualize what's going on here. Now they've asked us to find the probability that x is greater than 5. So let's do that. Let's mark x 5. X equals 5 is somewhere in here, right? So the probability that a randomly selected item will fall in this range to the right is over here. So we're looking for this. This is the probability that x is greater than 5. So remember, we can use norm.dist like we said we were going to, right? Finding a probability is the same thing as finding an area, which means we use norm.dist. But norm.dist will give us the left area and since the area we want as our final answer is the right area, then subtract it from 1 to get the right area. Okay, so that's our strategy here. All right, so we're going to be doing norm dot dist with boundary of 5, mean of 4.6 and a standard deviation of 1, and true for cumulative. Okay, then we're going to subtract from 1 to get the other side. So this left-handed area, or sorry, I meant to say this, I meant to say that we're going to find this side, the left-handed area over here, and then subtract it from 1 to get the answer we really want, which is on the right. So the left-hand area is norm.dist, 4.6, mean, no, 5 is the boundary, 4.6 is the mean, 1 is the standard deviation, true for cumulative. Okay, so this side, notice, is 0.6554, which is a little bit more than half. And half, 0.5, the left side would be 0.5 when you get to the mean. So this answer is reasonable for the left side. Okay, now if we subtract from 1, this answer, we get this is our final answer, which is, again, makes sense because it's, since our boundary is to the right of the mean, then we know this right shaded region is less than 0.5. So that makes sense. That should be correct. So we'll go over and put that into 3 decimal places. Let's see. The 5 to the right of the 3rd decimal place tells us to round up. There we go. All right, now number 24 from lesson 8. Engineers must consider the breadths of male heads when designing helmets. The company researchers have determined that the population of potential clientele have head breadths that are normally distributed with a mean of 5.8 inches and a standard deviation of 0.9 inches. Due to financial constraints, the helmets will be designed to fit all men except those with head breadths that are in the smallest 2.5% or the largest 2.5%. What is the minimum head breadth that will fit the clientele? And also, what is the maximum head breadth? And enter your answers accurate to 1 decimal place. Answers obtained using exact z-scores or z-scores rounded to 3 decimal places are accepted. Right, so this is basically telling me that we might actually be better off using the z-score table. Okay, well, let's see. We can do both. Or just round them to 3 decimal places like it recommended. All right, so let's set up our curve. It says that we are dealing with normally distributed, so it's going to be a bell curve. We have a mean of 5.8, standard deviation of 0.9. And we want the smallest 2.5% and the largest 2.5%. What we want to do is find out where those cutoffs are. So we have the mean given as 5.8. We have the standard deviation of 0.9. And we want the, basically, we want the percentile for 2.5. The 2.5th, which is kind of a weird thing to say, 2.5th percentile. And then we also want the positive twin on the other side. So the small one will be negative, but the larger one will be the same value, just positive. And here's how I know. They're asking if this is our curve, we have some x value over here, and this area to the left of it is the lowest 2.5% or 0.025 as a decimal probability. And the upper 2.5% is going to be a value over here to the right of the mean, so it'll be positive. This one will be negative, but they'll be the same distance from 0 because the normal curve is symmetric. So if the left tail over there is 0.025 and the right tail over here is 0.025, then these two values lie the same distance away from the mean. And the mean is 5.8. Okay. So remember, if you're looking for a boundary, and you have a left area, as we do here, 0.025, then you will use norm dot inverse. The left area, the mean, and the standard deviation. Okay. It should have given me a negative value, but I guess something is definitely off about that. 0.025 should have given me a negative boundary. For this one, it should be the same answer but positive, but this one's already positive, so what's going on? It's very strange. But this answer does make sense if you just make it negative. Oh no, it doesn't make sense. I'm sorry, I'm thinking wrong. That would be true if these were z-scores. You would get a negative and a positive. But they're not z-scores. What are they in fact in this problem? Head breadths. Head breadths can never be negative. You know, z-scores are standardized to tell you how many standard deviations either above or below the mean you are. And if you're below the mean, then it'll be a negative number. It's a value of relative placement. That's a z-score. But x values, they represent whatever it is that you're measuring. So having a head breadth that's negative would, of course, make no sense. So we're going to have to, we're not going to be able to just do what we would do if we were dealing with two z-scores and find one and make the other positive. Here, we get the left area, or we got the left answer pretty quickly doing this, but we're going to have to be a little more clever getting the right answer, the right boundary, the maximum. So this is our minimum head breadth of 4.036, what is it, centimeters? Inches. Okay, so that's the minimum head breadth that will fit the clientele. And it says round it to 1 decimal place. So when we round to 1 decimal place, you can see that the 3's to the right of the 0 is not going to have us round up, so that's how it becomes 4. Okay, now for the maximum. Because we can't simply just change the sign on this, we're going to have to be smarter. We're going to take this area. I got to figure out what this area is so that we can use it in our norm.inverse function, because norm.inverse always needs a left area. Okay, now we know that the whole area under the curve is 1, and we know that the right area here is 0.025. So this area over here is 1 minus 0.025. So what does that equal to? One minus 0.025 is 0.975. So to find my answer here, the maximum will be norm.inverse 0.975, mean of 5.8, standard deviation of 0.9. So 7.56 inches. I'm going to round this to 1 decimal place. The 6 to the right of the 5 tells us to round up. 7.6 inches. Okay. And then we have one question from lesson 9. The population has parameters mu, mean 58.7, and sigma, the standard deviation, 52.3. You intend to draw a sample of size 133. What is the mean of the distribution of the sample means? Okay, this is using the central limit theorem, which is explained here. The sampling distribution, where you're looking at the distribution of sample means. So this is where you take multiple times, or as many times as you can, every possible sample of a certain size from a population and calculate the mean. Then you save all those means and they make their own distribution. So we're not talking about the distribution of x values here. We're talking about the distribution of all possible sample means of a certain sample size. Well, they follow the same distribution as the original X does, according to the central limit theorem, but only if one of these two things are satisfied. Either the sample size is greater than 30, or if you happen to know that the individual values came from a normal distribution, then it'll automatically be true that the means are also normal and follow this. So looking at this problem here, we have a sample of greater than 30. So it's the central limit theorem is definitely going to hold here. So now we know that the mean of the sample means is going to be the same mean of the original distribution, and the sample standard deviation of the sample means is going to start with the same standard deviation as the original population, but then divide by the square root of n. So the first part of this problem is easy. We use this same mean of the original population. But for the standard deviation, we just have to take this number, 52.3, which is the original standard deviation, and divide it by the square root of n. So we're going to do that before we do anything else. Okay, so the standard deviation is going to be 52.3 divided by the square root of 133. Accurate to 2 decimal places, it's 4.53. And that's the whole premise for lesson 9. Is any of the problems in lesson 9 are going to involve using an adjusted standard deviation, dividing by the square root of n. And everything else works pretty much the same way as it did in lesson 8. But you do need to check those conditions, that either your sample size is greater than 30, or make sure it's stated in the problem, or that you're able to verify with like a histogram or something like that to tell if it's bell-shaped. Usually it'll just be mentioned in the problem that it's from a population that's normally distributed. And if it's not mentioned, then you have to have a sample size that's greater than 30. So what I typically do is I just first look for the sample size to be greater than 30. If it is, you don't even have to check if it was originally normal. If you don't have a sample size greater than 30 and it also does not say somewhere that it's normally distributed, then probably you're out of luck and you can't use this theorem. But that's very, very rare. So I hope this helped. Those were all the questions in my inbox. And I will see you guys next week.